Hello, this is Dr. Michael Hassan, the Engineering Doctor with Innovate. This is presentation number 3. The title of the presentation is Decision Making. This is a disclaimer for you to read. The objectives of this presentation are: we'll start with the introduction. We try to define inference, reasoning, and decision making, uncertainty, expert system, intelligence system, and DM application, which is decision-making applications. Decision-making in classical logic, review decision-making techniques under uncertainty, review of Dempster-Shafer belief theory, and we'll use Dempster-Shafer theory in object and target recognition. Inference is a conclusion reached on the basis of evidence and reasoning, or the process of reaching such a conclusion. Example: all humans are mortal. All Canadians are humans. Therefore, all Canadians are mortal. So we inference, actually, we did not say that all Canadians are mortal. It was not given as an input knowledge. However, the reasoning, if all humans are mortal and all Canadians are humans, therefore all Canadians are mortal. Inference mechanism represents the logical unit by means of which conclusions are drawn from knowledge base according to a defined problem-solving method. Example: so the facts P and Q, the rule of P and Q, then on. Reasoning could be deductive. Reasoning is a process by which thinking moves from one idea to a related idea or ideas that lead to a conclusion. Deductive reasoning, where conclusion follows necessarily from stated premises. For example, premise 1, all humans are. Premise 2, Gilgamesh is a human. Conclusion: Gilgamesh is mortal. Reasoning could be inductive. Inductive reasoning is a form of inference producing propositions about an observed object based on previous observations. As an example, the premise is the sun has risen in the east every morning up until now. The conclusion: the sun will also rise in the east tomorrow. Reasoning could be analogical reasoning. Analogical reasoning is a weaker form of deductive reasoning and often leads to wrong conclusions. For example, if we say premise number 1, Shakespeare is a human and male. Premise number 2, Madame X is a human. Conclusion: Madame X is male. And this is a false conclusion. So analogical reasoning may lead to false and wrong conclusions. Now, reasoning could be abductive. Abductive reasoning starts with incomplete set of premises, and the conclusion does not follow with certainty its premises. For example, premise 1, a patient has a headache. Premise 2, the patient has high temperature. Conclusion: the patient probably has flu. So this conclusion does not follow with certainty its premises. So the patient may have flu or may not have flu. False and could be wrong. Reasoning, fallacious reasoning, commits a formal fallacy or an informal fallacy. Formal fallacy occurs when there is a problem form or structure of the argument. For example, the new employee is too quiet and has no sense of style. We should fire him. Informal fallacy is an error in reasoning that occurs due to a problem with the content rather than the mere structure of the argument. For example, dogs are good pets. Coyotes are dogs. Therefore, coyotes are good pets. And this is again false. Decision-making is a process that results in the selection of a belief or a course of action among several alternatives. So we have 1,000 alternative, but only one solution within this 1,000 needs a decision-making process, which is a very tedious process to reach that conclusion. Every decision-making process produces a final choice. Real-time decision-making is achieved when the final choice is generated in real time or immediately, or in less than 1/60 seconds. Uncertainty is the inability to predict the future behavior of a system. This inability is seen as arising from a lack of information, incomplete information, partially wrong information, and partially occluded information. Uncertainty can be grouped into 3 types based on the type of information deficiency. 1. Measurement uncertainty. Any measurement is limited in its accuracy. This uncertainty can be reduced but not eliminated by improving the measurement process. Example: poor background, imperfect sensor, bad measurement condition, etc. all may generate measurement uncertainty. Number 2, epistemic or lack of information uncertainty. We cannot be certain about what we do not know. Lack information uncertainty can be reduced by expanding more resources and more sensors to gain more information. And even we can include sensor integration, where we integrate a variety of sensors to generate one signature information about the object or the subject matter. Occluded object, dirty or greasy backgrounds, imperfect object, etc. are examples of epistemic or lack of information uncertainty. Number 3, stochastic uncertainty. This uncertainty results from inherently random part of a system or process. In this case, uncertainty that appears to be stochastic is in fact due to a lack of information. Alternatively, measurement error may give rise to an apparently random distribution. Example: statistically variable objects represent actually stochastic uncertainty. What's an expert system, and what's the difference between an expert system and an intelligent system? An expert system is a computer system that emulates the decision-making ability of a human expert. Intelligent system is an efficient expert system with feedback mechanism, using data mining and machine learning approaches. Expert system is divided to 2 subsystems: knowledge base, which is facts and rules, and inference engine, which applies the rules to the non-facts to deduce new facts, or to come with conclusion. Decision-making application. There are numerous applications based on decision-making. The first one, interpretations. Inferring situations, descriptions from sensor data. Voice, speech recognition, object and target recognition. Hearsay is a pattern recognition system, speech recognition system, a stream of noisy voice data. Predictions, inferring likely consequences of given situation, like pattern-based risk assessment. So predictions is a second application of decision-making theories. Diagnosis, another application, inferring a system malfunctions from given observations. There are many medical diagnosis systems like CADU, CEUS, MICIN, ICIN, PUFF, PUFF, and Sterile, an Italian system, landslide safety and for monument safety, dam safety. Another application is design, configuring objects under constraints. And like the DENDRAL, developed beginning in 1965 by AI researcher Edward Friedman and the genetics Joshua Lindenberg, both of Stanford University. Heuristic Denadrill, later shortened to Denadrill, was a chemical analysis expert system. Mortgage Loan Advisor R1 is a rule-based manufacturing system that has much in common with other domain-specific systems. SID, Synthesis of Integrated Design, is a knowledge-based system used for the synthesis of logic designs. Another application is planning designing action, like mission planning for autonomous underwater vehicle, monitoring, comparing observation to plan vulnerabilities. Reactor is an expert system for diagnosis and treatment of nuclear reactor accidents. Another application, debugging, providing an incremental solution for complex problems. Examples on this, we have Saint, MATLAB, and Maxima. Maxima is a prototype expert system for the treatment of certain nonlinear filtering problems, described with illustrative examples. MATLAB is mathematical expert system. Saint, developed at MIT, constructed. Saint is the acronym for Symbolic Automatic Integrator, and it is acknowledged at first expert system as the first expert system. So Saint is acknowledged as the first expert system, and is symbolic automatic integrator. Repair is another application executing a plan to administer a prescribed remedy. As in the example, toxic spill crisis management. Instructions, diagnosing, assessing, and repairing student behavior. There are existing systems, expert systems, and student behavior like SMH, PAL, and like STEAMER, STEAMER, which stands for Interactive Inspectable Simulation-Based Training System to serve as a tutor, training students in the principles of propulsion engineering. Another application is control, which is interpreting, predicting, repairing, and monitoring system behavior, like real-time process control. As we see, actually, there are many applications for decision-making theories, and these applications make decision-making a very attractive subject in machine learning, expert systems, and intelligence systems. Decision-making in classical logic. Classical logic ignores uncertainty. Propositions are either true or false. T for true, for false. The implication relationship between antecedent P and coincident Q is equal to not P or Q. Hence P leads to Q, called modus ponens, and not Q leads to not P, for not P, modus tollens. So as you can see, if we have P and Q, and this is a modus ponens, which is P, then Q leads to Q, and if P and Q is false, false, okay, then what we have not P or Q will be true, and so on and so forth. So P will be leading to Q will be equivalent. So if it's true, true, not P, which is false, or true, which is true. Now, decision-making techniques under uncertainty, we have Bayes' theorem, we have Meisen, which is the medical diagnosis system, possible inference, Dempster-Shafer theory, Inferno, we have possibility theory, fuzzy set theory, quantum cognition, and we have the info gap decision theory. We will concentrate on Dempster-Shafer belief theory because it can handle uncertainty very effectively and successfully. Also, some AI scientists question the accuracy of numeric approaches, and hence they propose symbolic approaches, decision-making, like linguistic reasoning, non-monotic logic, and truth maintenance, and the theory of enforcement. So as we can see, there are many decision-making theories and approaches which will allow you to make decisions. Dempster-Shafer theory is based on expansion-based theory. So for a set of mutually exposed hypotheses H, which is a set of H1, H2 up to Hn, distribution of belief of the hypothesis set is called basic probability assignment function M, which has to satisfy the following conditions. The membership value or the evidence value of any focal element A will be between 0 and 1 for all and each A in H, the set of hypotheses H1, H2 to Hn. The membership value, evidence value of no member will be equals to 0. And the sum of all membership of A will be equal to 1. L A in H for every A in H equal to 1. So 1 will be represent true, and 0 will represent false. And we have values between 0 and 1 will represent a partial evidence, and this is why Dempster-Shafer theory is an extension of Bayes' theory, and then it's also an extension of the standard logic theory that we just actually referred to in the classical decision-making in the classical logic. Because in the classical logic, we have either true or false, or 0 or 1. Now, Dempster-Shafer theory, any subset A of S says that M of A is greater than 0 is called a focal element. A belief structure is called Bayesian if each of the focal elements contain a singleton, one and only one hypothesis. Uncertainty in proposition is characterized by two values: the degree of belief, which is a measure of evidence for the proposition, and possibility, which is 1 minus the measure of evidence against the proposition. Now, Dempster-Shafer belief theory, which started with Dempster, then Shafer was a rule of combination to aggregate multiple evidence. The new belief function is the orthogonal sum of systemic belief function. So to combine membership 1 for object A1, A2 up to 2K, membership 2 for object B1, B2, and Bn, M12 is defined as following: is the sum of M1AI, M2BI for all the intersection of AI, Bj is in C, in the real set of hypotheses, divided by a normalizing factor, which is 1 minus the sum of M1AI, M2Bj, AI intersection of Bj is equal to phi, which is the empty set. So those are the evidences which do not contribute to any object. So 1 over 1 minus, so this is 1 over 1 minus this value, which is k, be equal to L. So L will be 1 over 1 minus k, where k will be equal to this value, or the sum of AI, M2 Bj, AI intersection Bj is equal to phi. Now, to understand this, we will have actually the membership evidences could be represented in two lines, horizontal line and vertical line. So we have M1, A1, M1, A2 up to A1, AK to be combined with M2, B1 up to M2, Bn. Now, as an example, with the three object or the three hypotheses, we will have M11, M2, M3 to be combined with M21, M22, and M23. Now, those squares, some of them contribute to the hypothesis. For instance, the hypothesis H1, B1. M11 and M21 contribute to D1 because both of them represent actually 1. M2U is the uncertainty value in those measurements. Those actually has to add up all of them to 1. So M21, M22, M23 plus M2U will be equal to 1. M11 plus M12, M13 plus M1U will be equal to 1. So this will be contributing to hypothesis D1, and D1 and also M2U multiplied by M11 contribute to D1. So while in D2, for instance, which is the second hypothesis, what the contribution is, it is M12 with M22, because if you look at the second 2, which is referred to the hypothesis, so this will contribute to D2. M12 with M2U, which was, this is uncertain, also will contribute to D2. Now also with M13, we will have M13, M23 will contribute to hypothesis D3, 3 with M2U will contribute to hypothesis D3. Now M1U and M21, this is contribute to D1. Why D1? Because the second one, if you look, D1 is the second one, which refers to the hypothesis. M22 with M1U will contribute to D2, and M1U with M23 will contribute to D3. However, M1U with M2U does not contribute to any hypothesis, so this will be capital MU, which is uncertainty. It is combined uncertainty. So by doing this, we can calculate the membership of evidences to D1, to D2, and to D3 in simple equations. Now, each M value could be evaluated based on a specific approach. So here we use a modified multivariate normal distribution to determine the value. So if I have 3 objects, each object could be defined by features. Each feature could be defined by the angle, which is the vertex, the angle of a vertex, and the length of the 2 sides surrounding this vertex. So this triangle is defined by 61,1, 61,1, and 61,1. So this will be the numerical representation of the equilateral triangle shown here. While this triangle defined by 45, 45 with the length of the line surrounding it. And this triangle, the same thing, defined by the degree for each vertex and the length of the 2 lines. Now we calculate actually the set of evidence for each one based on multivariate normal distribution. So we can calculate M12, M21, M22, all these values accordingly, okay, so this is really would be referred to it, we can refer to it to D1, D2, and D3. So we can calculate the evidences based on comparison of each vertex with the following. For instance, if this is M1, if this is D1, so if we compare this, which is 61, this vertex with this one, which is 45, 1, and root 2, 1.42, we will calculate M12, calculate M12. and here we'll calculate M1. So by taking M12, so M1, so we can calculate M12, M13, and so on based on the object that we do comparison with by using the multivariate distribution. Now mu1, sigma 1, mu2, sigma 2, mu3, and sigma 3 are constants based on sigma 1, sigma 2, sigma 3 are constant, where mu1 and mu2, mu3 are values featured in the second object or the third object, and so on. So we can calculate, as we said, M1 and M2, and by combining M1 and 2, we will end up with M1, 2. Then we combine with M3, we end up with M13. And M13 will give me the final set of evidences that we are looking for. So by using really the Dempster-Shafer of evidence will allow us to calculate the mutual evidence for each object, and by comparing the object with other object, we can find the corresponding membership of evidence for that object. So as an example, we have a set here of images as our database. So we have pliers, a cutter, and a wrench. We will model those. We will find all the description of these objects, okay, based on their numerical description. Then we'll have an input images, and we try to find a match between the input image and those objects by using the Dempster-Shafer theory. So in the first, let's look at the last scene where we have the input is basically a cutter. So this is the last figure. So as a cutter, we will have the evidence produced is 0.988 as a cutter, while it is really negligible values at a wrench or as a pliers. Similarly, if I have concluded or two objects in the scene, like this one, with a cutter and a wrench, give me 0.55 as a wrench and 0.55 as a wrench. We are looking at 0.29 as a wrench and 0. I do apologize. This is the figure here. So here 0.29 as a wrench, 0.703. So it is a satisfactory detection to object and a negligible value as a pliers. And so on and so forth. If the input is a pure cutter, for instance, okay, if it's a pure cutter, the evidence calculated as a pure cutter is 0.985, negligible values as pliers and as a wrench. So by doing this, Dempster-Shafer theory allowed me to detect any input object to this expert system by determining the factors of evidence with confidence in that object. So by determining those values, we can have a successful match. I thank you so much for listening. Please subscribe. See you soon. Sincerely, Dr. Hassan.